All right, Fafan. Then let's see. That's calculus. We are starting with limits of a function. Limits of a function. I believe you've done functions, right? So you know what a function is. Yeah, you know what a function is. Function. Let's say I'm dealing with one variable, so f of x, right? So we have the, let's say the domain and the codomain, right? Then we have an object inside the domain which is x, then the codomain which is y. So if this object x maps onto this one and only one variable in the codomain, so then we term this as a what? As a function. So that means it takes only one element from the domain to the what? Codomain. One-to-one function. Alright, so now don't let us go there. Let's talk of limits. Limits. Now, in calculus, you can't dodge limits in calculus. Yeah, when you talk of limits, it tells how the function behaves as the variable. So let's say the variable x or y approaches, let's say, a point or a larger number. So let's see something here. If I have f of x to be equal to 3x plus 4, f of x to be equal to 3x plus 4. Let's say when I give you an x value, which is x equals, let's say, 4, an x value, let's say x is equal to what? 4. So this one, it means that wherever I see x, I'm placing what? 4 inside, right? So this one, it tends to be what? F of what? 4, right? I'll plug in what? 4 into where I see what? X. So which must be equal to what? 3 times 4 plus 4, right? So you have f of 4, which is equal to 3 times 4, which is what? 12 plus what? 4. So 12 plus 4 gives what? 16, which is equal to what? F of 4. So it means that as this x approaches 4, or when you plug in this 4 into the function, this function tend away to what? 16. It tends to what? 16, right? So if you plug in any value of x, this function behaves, it changes. You can plug in -1, you can plug in 4.01, you can plug in 3.092. You see the behavior of this function. So when you talk of limit of a function, as x approaches a certain value, then that means that function, how the function behaves as x approaches what? A certain value. That's what we mean by what? Limit of a function. So now let's come to calculus. Let's see. When you come to calculus here, let's come to calculus. If I have this f of x equals, let's say, 4x plus 30 as x approaches, let's see, -4. So this, we have f of x equals 4x plus 3 as x approaches what? -4. I believe you know, wherever you see what? X, you plug in what? -4, right? So you see what? The behavior of this function here. Now let's see something. So now the limit, write it as lim. The limit of this f of x as x approaches what? A. As x approaches a of this f of x. So that's what we mean by what? Limit here. The lim of f of x as x approaches what? a certain what point, right? Okay, so now let's start wrapping up. Let's start wrapping up. Let's start something. So if you have this limit this one is read as well. The limit of f of x as x approaches what? A. So what will be the value? The limiting value, that's what? L. What will be the limiting value of this what? F of x as x approaches this certain what? Value. What will be the behavior of this what? Function. Do you understand that? Alright, so now if I have the limit of 4x plus 1 as x approaches, let's say, negative 2. How can you evaluate this, or how can you work this out? So what will be the limit of this 4x plus 1 as x approaches what? Negative 1. This is a function, that's a linear function, because the variable x, the highest power is what? 1, right? So now, let's see. So now, wherever you see x, you plug in what? Negative 2. So you have limit as what? 4 approaches what? Negative 2 plus 1. So, negative 2. So we have what? 4 times negative 2, which is what? Negative 8 plus 1. So you get what? Negative 7. So that means the limiting value is what? Negative 7. So as x approaches this function, this f of x function, of what? Negative 2, the limiting value will be what? Negative 7, right? The limiting value will be negative 7. So now, let's see. Alright, so now let's start something important. Here. This is just the introduction here. I was just explaining from JHS you did number plane, then SHS you did coordinate geometry, you did functions, you did functional notation. So you know f of x, let's say find f of 2, f of negative 1. You know wherever you see x, you plug in that. So it means how the function will behave as you plug in a certain what? Value. You understand that? So now let's start the ball rolling. So let's start with limits of a function at infinity. Limits of a function at infinity, right? Limits of a function at infinity. So now, this is the symbol used to represent what? Infinity. That's the symbol for infinity.
What's that? I need to know.
That's infinity. Alright, so let's continue. Let's see the limit of f of x as x approaches infinity. What will be the limiting value of that? Now, this one we are talking of what? The function f of x. The limit. Find the limit as x approaches a larger number. This one is a larger number. That's the symbol for infinity, not infinity. So that's the symbol for infinity. So that's a larger number, right? A larger number. So what will be the behavior of the function as x approaches what? A larger value or a larger number. All right. So let's see that quickly. So limit of a function at infinity. So we have to get some certain rules for limits so that you understand. You don't do limits as we are doing just like that. You have to get a certain rule, a certain law that will guide you to understand limits properly. So now we are starting with rules for limits of functions at infinity. Rules for limits of functions at infinity. Rules for limits of functions at infinity. So number one rule, we have limits. Number one rule, we have limits as x approaches infinity of k. As x approaches infinity of k equals k, where k is a constant, where k is a constant. So we have this, the limit of this k, where k is a constant. A constant means a value 2, 3, 4. So what will be the limiting value of this k as x approaches infinity? It will be the same with k. So where k is a what? It's a constant. We'll be solving more questions so you know what we mean here. 2. The limit as x approaches infinity of 1 over x exponent p. The value is 0. What will be the limit of this function 1 over x exponent p as x approaches what? Infinity. It will be 0. Where p is a positive constant. You understand this? I'll use calculator to teach you this. If you have the limit as x approaches infinity of 1 over x to the power p. Now the denominator here, x to the power p, is an exponential function, right? 2 to the power 3. Now let's see. 2 to the power 3. You have 2 to the power 3. Then we have 2. Which one will move faster? Which one will approach infinity? It's 2 to the power 3 because this one tends to be what? A larger number, and this one tends to be what? A smaller number. So this one will be 8, then this one will be what? 2. This one is greater than that. Right. So as you take the limit of this function 1 over x exponent p of this x as x approaches what? Infinity of this function, the whole function will tend to what? 0. The whole function will tend to 0. Let's see. Let's see the third rule. The limit as x approaches infinity of 1 over k exponent x, which must be equal to 0 again, where k is a constant. where k is a constant, where k is a constant, where k is a constant, and k is greater than 1. When k is a constant and k is greater than 1. Where k is a constant and k must be what? Greater than what? 1. Now, I've told you that this infinity is a what? It's a larger number, a larger value. So when you plug in this infinity here, and when k is greater than 1. Now, the reason why we are saying that k is greater than 1 means we know that 1 to the power 3 billion or 3 million is the same thing as what? 1. So now, we have to what? Ignore 1, then we concentrate what? 2, 3, 4, 5. Then we see the behavior of this function as x approaches what? Infinity. So when you say that k should be 1, then the function is the same, because we will get what? 1 over 1, which will get us back to what? Rule 1, which means what? The limit as x approaches infinity of k must be equal to k as that, right? So we have to state the condition here that k must be greater than what? 1. K must be greater than what? 1. What would be the limit of that? All right. So copy it down, copy. Let's see the fourth rule. The fourth rule. Let's see the fourth rule. The fourth rule. The fourth rule. It says what? The limit as x approaches infinity of f of x plus or minus g of x, what will be that? So now here, the limit as x approaches infinity of this f of x plus or minus g of x. I believe you know from, let's say, the general quadratic formula, we know x must be equal to plus, x equals minus b plus or minus. You do for what? Plus, then you do for what? Minus, right? So it's the same thing here. It's the same thing here. So now we can concentrate and we can say that this one must be equal to, let me take the positive aspect. So it will be what? We have two functions inside the bracket here, right? So I'm taking the positive aspect. We have two functions here. So I'll say that the limit as x approaches infinity of this f of x plus the same thing, the limit as x approaches infinity of this g of x. So this is what it means for this. I'm taking the positive aspect. So let's see the negative aspect. It's the same thing as what? The limit as x approaches what? Infinity of f of x minus the limit as x approaches what? Infinity of what? G of x. So that's how it goes. That's how it goes. So when you get two functions and they tell you to take the limit as x approaches infinity, you have to take it one after the other. As the limit of this f of x as x approaches infinity plus, you don't get two operational signs here, you get only one operational signs. But here in teaching, that's why we brought what? Two operational signs here. So plus the limit as x approaches infinity of this g of x. Then we take the negative aspect too, which is the limit of this f of x as x approaches what? Infinity. Or you can say the limit as x approaches infinity of this f of x minus the limit as x approaches infinity of this g of x. So that's the rule what? 4. Rule 4. Rule 4. Rule 4. So this one is sum, then what's different. So when you get a function like this, this is how you treat it. Or when you get a limit function as this is how you treat it. Let's see rule 5. Rule 5. Rule 5. Rule 5. Rule 5. It says what? The limit as x approaches infinity. The limit as x approaches infinity of this f of x finds this g of x. The limit as x approaches infinity of this f of x times this g of x. So we have product here, right? So now, how do you treat this? It means you have to take it again as the limit as x approaches infinity of this f of x times the same thing, the limit as x approaches infinity of this g of x. Very, very simple. The limit of this f of x times the g of x is the same thing as x approaches infinity. Is the same thing as what? The limit of this f of x as x approaches infinity times the limit of this g of x as x approaches what? Infinity. So that's that. Alright, so now let's see. The sixth rule for that. I believe you are getting what we are doing. So these are the rules you have to take note. The rules of functions, of limit of a function, you have to take note. It's very, very simple. It's not difficult. So now I'm here. 6. Rule 6. The limit as x approaches infinity, the limit as x approaches infinity of this k times g of x. So this is how the thing is. The limit as x approaches infinity of k times g of x, provided k is what? A constant. So provided k is a constant, or where k is a what? Is a constant. Where k is a constant. A constant means what? Value, right? So now let's go. We all know that this one is product, right? We can say that the limit as x approaches what? Infinity of k times the limit as x approaches infinity of the g of what? X. So the limit as x approaches infinity of this k times the limit as x approaches infinity of this g of x. We all know that when we are taking the limit as x approaches infinity of a constant is the same thing as what? K, right? So you get k times the limit as x approaches infinity of what? G of what? X. As that. So as that. So when you visit books from certain books, or when you visit various books, you know that they didn't bring this. They just wrote that is equal to k times the limit as x approaches infinity of this g of x, because the limit of k as x approaches infinity is the same thing as what? K. So we get it as that, right? Alright, so that's the 6th rule. Let's see the last rule, which is the 7th rule. The 7th rule as that. The 7th rule. The 7th rule. We have the limit as x approaches infinity of f of x all on g of x, provided g of x, provided this g of x, where g of x must not be equal to 0. Because if this g of x be equal to 0, then it becomes what? Undefined, right? Does not exist, right? So let's see. So let's see, provided this g of x should not be equal to 0. Now, the limit of this f of x over g of x, that's a rational function, right? As x approaches infinity. So how will you tackle that to get the limiting value, L? So it's the same thing as you take it one at a time, which is the limit as x approaches infinity of this f of x all over the limit as x approaches infinity of this g of x. So you find the limit of the numerator, the function at the numerator, then also you find for the limit at the function at the denominator as x approaches infinity for each of them. So that's how you work that. So where this limit as x approaches infinity of g of x should not be equal to what? 0. It must not be equal to 0. It must not be equal to 0. So that's that. So now we can start with examples for rules for limits of functions at what? Infinity. So now we can start with questions or examples, limit of a function at what? Infinity. So that we'll know how to solve them properly. So let's start. Let's set the ball rolling. Very, very simple. So I just try, let's say, okay, for this one is calculus, right? It's calculus. So you cannot skip calculus without limits. Because what is calculus? I didn't explain what calculus is. Calculus is a branch of mathematics that deals with what? Derivatives and what? Integrals, right? It deals with the derivatives and the integrals. That's calculus. It's a very, very nice topic. Very, very interesting. We have to love it because it's very, very nice. Alright, so let's start with examples. Examples of that. So question 1. They said find the limit as x approaches infinity of this 1 minus 2 on x cubed if it exists, provided if this function exists. We should find for the limit. So now let's see. We can find for the limit. Now, is it the fourth row or the third row? We have the limit as x approaches infinity of this 1 minus 2 on x cubed. Now this one, we can work it as what? Let's break it down, which is what? The limit as x approaches infinity of what? 1, right? So this one minus, we have the limit as what? X approaches infinity of what? 2 on x cubed. This one. 2 on x cubed. So we have it as that. Now, the limit as x approaches infinity of 2 over x cubed. Now let's see this one. The limit of 1 as x approaches infinity is the same thing as what? 1. This one is a what? It's a constant. It's a value. There is no x depending on this one here, right? So it's a constant value. So we get what? 1 minus the limit as x approaches infinity of 2 on x cubed. Now, I told you that this infinity is a what? It's a larger value. So let's see something here. Take your calculator. You take your calculator and let's see something. We have 2 over x cubed, right? So wherever you see x, we are placing in what? A larger value, right? We are placing in a larger value, a big number. So let's see, 0.2 on, let's say, we are taking the larger value to be 100 to the power 3, right? And let's see the behavior of this function, right? Okay, so 2 on 100 to the power 3. So we had what? we had 2 times 10 to the power of negative 6. 2 times 10 to the power negative 6. And this one is in standard form, right? When you are changing it to an ordinary number, this one, 2 times 10 to the power negative 6. It's the same thing as 2.0 times 10 to the power of negative 6. Now, let's change this number, this standard form number, to an ordinary number. So, or this scientific notation to an ordinary number. Now, if you check the power of 10 is negative, which means that this point is coming from what? The left, right? The left-hand side. So we are moving it back. And if you are moving it back, you check the number of times you are moving this point. So the number of times I'm moving this point is what? 6. So I'm moving from right to left. And when you are moving from right to left, the power of 10 is what? Positive what? 6. So they will cancel out. So I'll get what? 1, 2, 3, 4, 5, 6. So I'll get as that, which is 0.1, 2, 3, 4. 1, 2, 3, 4. So 1, oh, this one. 1, 2, 3, 4, 5. Then 2. So 0.00002. So this one is closer to what? 0. It's closer to 0 because 0.0002 is closer to 0. So that's why we are telling you that the limit as x approaches infinity of this 2 on what? S cube, where this 3, the exponent 3, is a what? It's a positive what? Constant. So that's it. So then that means when you take in or when you put in this value, this larger number, the behavior of this function will approach what? 0, or will turn this, the whole of this function to what? 0. So we get what? 0 as that. So 1 minus 0 gives what? 1. So that's how to solve this question here. That's how to solve this question. It's very, very simple. It's very, very simple. It's very, very simple. It's the same thing as that.
Good afternoon. But I'm communicating with
All right. So if you have any question, you can send it to me so that we talk. So now, so the second one, which is fine. Let's see the second example. Second example. The second example. You should find the limit. So you should find the limit as x approaches infinity of this 2 to the power negative x plus 3. If and only if this function it exists. Because there might be a case this function will not exist, right? So now let's see what will be the behavior of this function as this x, this value x, approaches what? Infinity. For the first example, we had the limiting value to be what? 1, right? So now let's see the limiting value. What will be the value as this x approaches infinity of this function? Now, solution here. We can do something to the function here. 2 to the power negative x. We have 2 to the power negative x, which is the same thing as 2 to the power negative x is equal to what? You can write it as 1 on 2 to the power x, right? 1 on 2 to the power x. This is the same thing as that. That's the inverse, right? All right. So 2 to the power negative x is the same thing as 1 on 2 to the power x. So you can take it as the limit as x approaches infinity of, so in place of that, I put in 1 on 2 to the power x, 1 on 2 to the power x, then plus 3. So now we can proceed as that. We can proceed as that. So with this, you can see that we take what? The limit as x approaches infinity of this 1 on what? 2 to the power x. So we say that the limit as x approaches infinity of this 1 on 2 to the power x, then plus the limit as x approaches infinity of what? 3. We have it as that. We have it as that. So now, the same thing here. For this limit of this first function here, the function here is what? 1 on 2 to the power what? X. 1 on 2 to the power x. That's an exponential function at the what? Denominator. And we are placing in what? A larger value for this power of this exponential function. The power will be what? A larger number. So now, take your calculator. Then let's punch in what? 100. And let's see the behavior of this function. 1 on 2 to the power x. So we are taking x to be, let's say, 50, right? That's a larger number. Alright, so let's say 1 on 2 to the power 50. So let's see the behavior of this function here. 1 on 2 to the power 50. So we are getting 8.881784 times 10 to the power negative 16. So it means that this one is approximately 0. It's 0. So it means that the limit as x approaches infinity, wherever you see x and placing what? Infinity, this function tends to be what? 0. Because we take this infinity as a what? As a larger number. So we get 0 here. Then plus the limit as x approaches infinity of 3. You know that this 3 is a what? It's a constant value. So now we get the same thing as the constant here. So 0 plus 3 gives what? Is 3. So that's that. Very, very simple. Very, very simple. Very, very simple. Alright. So now let's see whether I'll get another question and then we solve. So that's it. So when you get something like this is how you'll be doing it. Now let's see another type of this limit of a function at infinity. Let's see another type of that. I always say that calculus is a jealous subject, or is a jealous topic, or is a jealous course. In fact, calculus is a jealous topic. Why? You can go and explain that. Why? Why is it that calculus is a very, very jealous topic? Jealous. So let's see the type 2. Now, we are considering the type 2 here. Type 2. So what we did was what? Type 1. So let's see the type 2. So the type 2, it reads as well. When the limits of the numerator and the denominator do not exist. When the limits of the numerator and the denominator do not exist, rule 7 cannot be what? Applied. I believe you know rule 7. We are taking the limit as x approaches infinity of that f of x all on what? G of x. So when the limits of the numerator and the denominator do not exist, rule 7 cannot be what? Applied. Full stop. In this case, divide the numerator and denominator by the highest power of what? X. In this case, divide the numerator and the denominator by the highest power of x. So that limit at infinity of the numerator, of the new numerator and denominator exist. I'll be giving examples and I'll be explaining here so you get to know what I mean. So again, I read again. When the limits of the numerator and the denominator do not exist, comma, rule 7 cannot be applied. Full stop. In this case, divide the numerator and denominator by the highest power of x, comma, so that limits at infinity of the new numerator and denominator exist. Alright. In general, comma, for all rational functions, I believe you know rational functions, it can be expressed as what? P of x all on what? K of x, where P of x is a polynomial, K of x2 is a polynomial, right? Alright. So, in general, for all rational functions, limits at infinity can be formed by what? Dividing the numerator and the denominator by a suitable power of x, usually the highest power. Again, in general, for all rational functions, comma, limits at infinity can be formed by dividing the numerator and the denominator by a suitable power of x, usually the highest power. So now, let's see what we mean here. So we have an example here. I said evaluate the limit as x approaches infinity of 3x all on x plus 2. That's the function given here. So we have this function here. So now, this one, when you see this, we can't apply rule 7 because you cannot take the limit as x approaches infinity of this 3x, then you take the limit as x approaches infinity of this x plus 2. Why? Because now, when you take the limit as x approaches infinity of this 3x here, when you insert a larger number, because there are a lot of larger numbers, right? The behavior of this function keeps on what? Changing. The behavior of this function keeps on changing because a larger number, it will approach what? To what? That larger what? Number. Because when I take the larger number to, let's say, 20, 3 times 20 will be what? 60. When I take the larger number to be 100, 3 times 100 will be what? 300. So it keeps on what? Increasing. It will increase. It will what? Increase. Do you understand that? So now with this, we have variable here, we have another variable, both the numerator and the denominator. How do we solve this? It says the variable, we check the variable with the highest power. The variable with the highest power. Now we have the variable here. What was the highest power? The highest power here is 1. So now we'll divide the numerator and the denominator by what? The highest what? Power. So we have this. It will be what? So we have solution to be the limit as x approaches infinity of this 3x all on what? X. We will divide this numerator by the highest power, which is what? X. Then divided by x on x plus 2 on x. So we have it as that. So this. So the limit as x approaches infinity of this 3x on x all over x on x plus 2 on x. So that's what I read. That's the meaning to what I read here. So now, this variable cancels that variable. And this variable cancels this variable. Right. So we have here to be what? 1. So I can say that the limit as x approaches infinity of what? 3 all on what? 1 plus 2 on what? X. What will be the limit as that? So for this, what will be the limit? The limit as x approaches infinity of 3 on 1 plus 2 on x. Of 3 on 1 plus 2 on x. What will be that? So now, okay, we are taking it now, we go back to our first example as what we did. Now we come down. If it is this, we divide by the what? Highest power. So our highest power is x. We divide here by x, here also by x, here also by x. So we have this. So now we go back to what we were doing, which is the limit as x approaches infinity of 3. Then all on the limit. So see, we have the limit. So when you are done doing this, you come back to the what? To the first example, or to the first type we were doing, which is the limit as x approaches infinity of 3 all over the limit of what? 1 plus 2 on x as x approaches infinity. So we have this. I believe you can remember. So this is what I mean here. So the limit as x approaches infinity of 3, you know that is what? 3. All over the limit as x approaches infinity of this one, it will be what? The limit as x approaches infinity of 1 plus the limit as x approaches infinity of 2 on x. I believe you are getting what we are doing here. So we move, which is 3 all over the limit as x approaches infinity of 1, which is 1 is a constant. So the same thing applies here. We get what? 1 plus the limit as x approaches infinity of 2 on x. So now let's see. The limit as x approaches infinity on 2 on x. So let's see. We have 2 over x. This time it's not 2 exponents x. It's 2 on x. So let's see. If you have 2 on x, right? 2 on x. Then this x, or this 2 on s, we can write it as well. 2 times 1 on x, right? Which is the same thing as 2 times x to the power negative 1. Which is the same thing as 2x to the power negative 1. As that. Right. We can write it as this. So this one is the same thing as that. Right. It's the same thing. So now let's see. I take s to be, let's say 2,000 or 20,000. Let's say when you take x to be 20,000, 2 on 20,000, which is what? 0.00 what? 0.003. 0.003. You can take x to be, let's say 10,000. 2 on, let's say, okay, let me give you 500,000. So still we are getting what? 0.00000004. So we can see that 2 on x, it's what? It's approaching 0 by the speed of which this function x approaching 0 is like, it's not moving slow, but it's not moving fast, it's moving what? Slow. But when you check the exponential function, it moves faster because this one is a linear. X to the power 1 is linear. But when you check the exponential function, the way this function will approach infinity faster than this. So this one, 2 on x, when you divide this infinity 2 over a larger number, you get what? A smaller number. That means the value is approaching what? 0. The value is approaching 0. So we can say that 2 over a larger number, the answer is what? 0. So when you get the limit as 2 on x, as x approaches infinity, the limiting value will be what? 0. So I have 3 over 1 plus 0. So which is what? 3 on 1. And 3 divided by 1 is the same thing as well. 3. Because 1 times what will give you 3 is 3. Very, very simple. Very, very simple. So this is how we work that. So when you get a variable at the numerator, then you get a variable at the denominator, you cannot use the root 7 to do it. You have to do some checks. Then you go back to the root 7, then you apply the laws of limits. You get that. All right. Let's go to another Question. Another question. We are still on the type 2. So we are done with the type 1. We are still on the type 2. Still on the type 2. Z, find the limit. Find the limit. We are finding the limit as x approaches